Okay, Riles. Today we're going to continue with trig, talking about trigonometric ratios of any angle. This means that we're going to have to build some new definitions. They'll seem new, but we'll learn we were actually using shortcuts for a couple. So let's review what we did in the last day, talking about angles in standard position, principal angles and related acute angles, and coterminal angles. Let's leave some space here because I want to do some calculations to show you why these angles are important. We didn't really talk about why they were important yesterday. So, standard position. Positive x-axis, positive y-axis, vertex at the origin. Here's 0 degrees, here's 90 degrees, here's 180 degrees, here's 270 degrees. If I was asked to rotate negative 230 degrees, I mean, I could try to picture it, and I think I see it as being 50 degrees past 180 degrees. But I might want to perform some calculations first. I might actually want to calculate my principal angle first by figuring out what would happen if I added 360 degrees, one full rotation to this. Yeah, that looks about right. So when I sketched 230 degrees, what I was doing was seeing that 230 is 50 past 180 degrees. So I actually found my related acute angle first. The related acute angle is 50 degrees. Okay. And then from my related acute angle, I could get my principal angle by doing, I'll show my calculations off on the side here. 180 degrees minus 50 degrees. That's 130 degrees. Okay. Now, I could have calculated my principal angle first by doing negative 230 degrees plus 360 degrees and getting 130 degrees, and then find my related acute angle by doing 180 degrees minus 130 degrees. In this case, it's 180 degrees minus 130 degrees because I want to know how short of a half rotation I am. Okay. So let's see. I got my related acute angle first by actually dropping the signs and doing 230 minus 180. And that gave me 50 degrees. Then I got my principal angle by doing 180 degrees minus 50 degrees. It's 130 degrees. We should remember to always show our calculations to our reader here. Okay. Now let's pick a trig ratio here. Let's look at the cosine ratio. And what I want you to do, grab a calculator, and let's calculate what the cosine of negative 230 degrees is. We'll approximate it. Then let's calculate what the cosine of 130 degrees is. And we'll approximate it. And then let's calculate what the cosine of 50 degrees is. And we'll approximate it. So you should trust that your calculator can do this. You're just typing numbers into your calculator and hitting buttons. But your understanding of what's happening might be breaking down a little bit. Because doesn't the cosine ratio measure the ratio of adjacent to the hypotenuse? But I don't have a right angle triangle with negative 230 degrees in it. So it's going to measure something for me here, and we'll talk about what it is shortly. Make sure I'm in degree mode. Cosine of negative 230 degrees. It gives me a decimal. It's about negative 0.6428. Trig ratios we want to be accurate with. We'll almost always keep it to at least 4 places. 3 is probably enough. 4 is safe. Watch what happens if I take the cosine of a coterminal angle. Cosine of 130 degrees is exactly the same. This is why coterminal angles are important. I'm rounding that up to 8. Yeah. Okay. If I were to do the cosine of 130 degrees plus 360 degrees, guess what's going to happen? I get the exact same value. Okay. These are the same. The trig ratios are the same because these angles are coterminal. Coterminal angles have equal trig ratios. Okay. And our new definition will explain why that's the case. Now, what about the cosine of 50 degrees? This is why we call this the related acute angle. The cosine of 50 degrees is going to be related to the cosine of 130 degrees and related to the cosine of negative 230 degrees because it has the same related acute angle. Now, it's not going to be identical. The cosine of 50 degrees is going to be a positive number. It's just the opposite of that right there. So it's very closely related. As far as ratios go, this is about the closest relation that you could have. If you're not the same, then at least you're the opposite. And that's because this is 130 degrees is related acute angle. Let's say ratios of related acute angles are, let's use the word, related to ratios of your principal angles. If we were to, say, take the cosine of negative 50 degrees, it too is going to be related to that. Look at that. It's the exact same value. What's another angle that has a related acute angle of 150 degrees? Or 50 degrees? How about 180 degrees plus 50 degrees? 230 degrees. Of course, the opposite of that angle right there. The cosine of 230 degrees is related to all of these. Sometimes it's positive, sometimes it's negative. We'll have to figure out why later. Okay. Oh, right. The reason why we don't want to measure this angle right here of 40 degrees, okay, the angle to the vertical, even if it's smaller, even if it's closer, is that the cosine of 40 degrees, I'm not going to say it's not related. It's just much harder to see the relationship. Doesn't seem to be related there. Okay. If I take 91 degrees, which has a related acute angle of 89 degrees, the cosine of 91 degrees is very closely related to the cosine of 81 degrees. 89 degrees. Did you see that? I guess you can rewind. I can't. The cosine of 1 degree does not seem to be related. That's why we always go to the horizontal, so that we get those related acute angles. Okay, so how are we going to deal with ratios where I can't make a right angle triangle, where I'm outside of the first quadrant? What we're going to do is we're going to learn the actual definition for these trig ratios. In previous courses, depending on your teacher, you might have only been working in the first quadrant, where you could always have a right angle triangle, and that's not going to be the case now. So let's draw an angle in the first quadrant. Don't make it look like 45 degrees, okay? Make it, I don't know, let's make it maybe bigger than 45 degrees. And it turns out that we can define angles by considering the coordinates of an endpoint on the terminal arm. It actually doesn't need to be an endpoint. It just needs to be along the terminal arm. Let's correct that. Coordinates of a point on the or along the terminal arm. We'll call this x comma y. Now you can still create a right angle triangle here by dropping a perpendicular down, finding the altitude there. But it turns out that trigonometry, which translates directly to triangle measure, actually has a little bit more to do with circles. That's supposed to be a circle centered at 0, 0. And so when I draw this circle, I recognize that I might not want to call this distance a hypotenuse anymore. I might want to call it the radius. Got an x value and a y value, and then a radius. And here's my angle of interest, theta. Now, the good news is you don't have to totally let go of SOHCAHTOA. If SOHCAHTOA has worked for you as far as a memory aid goes, then you can still use that. It reminds you that the sine of theta is the ratio of the opposite to the hypotenuse. But to get out of the first quadrant, all we need to do is label that, okay, well, look at my opposite side. I suppose my opposite side is going to be given by the length y, the y coordinate of a point on the terminal arm. And the hypotenuse is going to be given by the same measure as r. In grade 10, in the first quadrant, the cosine of theta is the ratio of an adjacent side of a right angle triangle to the hypotenuse of a right angle triangle. In any other quadrant of any other angle, my adjacent side is going to be given by my x coordinate. And my hypotenuse is given by the length of the radius. And the tangent ratio, the tangent of theta being the ratio of the opposite to the hypotenuse, well, we can change that by looking at the ratio of opposite to hypotenuse, the ratio of y 2x. Students don't always like change. People don't always like change. So right away, you might be saying, well, I like SOHCAHTOA better. There's a couple of things to say here. First off, we will need this. And second of all, this is actually the true definition. Okay, SOHCAHTOA is like training wheels. That only works in the first quadrant. This is the definition of what the sine of theta is measuring. We can look back here and say, oh, that's why the cosine of 130 degrees was negative, because we're looking at the ratio of its x value, which is negative. How could a side length of a triangle, how could the side length of a triangle be negative? It can't. How could an x value be negative? Well, it's easy if your point is to the left of the y-axis. Okay. Students like SOHCAHTOA because it's fun to say and it's easy to remember, I suppose. You can try building a memory aid here. If you write out, SOHCAHTOA comes from SOHCAHTOA. Not all grade 10 teachers bother teaching SOHCAHTOA. Some grade 10 teachers only do this because it works just fine in any situation there. Your memory aid here, try writing out SYRCXRTYX. And phonetically, I guess you would read it Sir Kixertix. I'm not sure how to spell it. Sir Kixer. You know what? I'm not going to spell it. Sir Kixertix. Sir Kixertix. There's usually students laughing at this point, saying Sir Kixertix sounds silly. But, like, do you realize how silly it sounds to say SOHCAHTOA as well? It's like, no, SOHCAHTOA makes sense. Sir Kixertix, that's pretty much the same thing. It's just a memory aid. We have to have these definitions memorized. Okay. Let's see how we use it. Now, try very hard to build an understanding of this. If you always want to go through SOHCAHTOA, you can always translate, but you want to immerse yourself in this language, and it's not that hard. So let's try. Sketch the angle passing through each, I guess, Cartesian point. No, we don't really need that there. And calculate theta to the nearest degree. So we will need a calculator here, but let's make sure we estimate our answer first. Theta is in standard position. We're going to open up a bit of a can of worms here and investigate what's happening in a little bit more detail in our lesson tomorrow. Or next day, 5.3. But so yeah, 4,7. This is going to feel pretty familiar because our terminal arm lands in the first quadrant. I don't need a grid here. I'm going to say, here, let's make that 8 and that 8. You probably want a square scale, unlike some of our sketches in other units. I'm going to go over 4 and up about 7 right there. Okay. There's 4,7. And instead of drawing a triangle, I could visualize drawing a circle, if you like. Okay. Now, we are equipped to use the tangent ratio. We might want to find the value for the sine ratio or the cosine ratio as well. Okay. If we are asked to find the sine of theta, then I look up my definition. Sir Kixertix, SYR, tells me that the sine of theta is going to be the ratio of y to r. I know that y is, or if y is 7, then x would be 4. I don't know my r value. The way that we're going to find r, in grade 10, we would have said, oh, we're finding the hypotenuse, so we use the Pythagorean theorem. The Pythagorean theorem with x, y, and r is going to be written r squared equals x squared plus y squared. The interesting thing, though, is that this equation right here is actually also the equation of this circle. So you don't need to be thinking triangles. Okay. Let's get r squared is going to be 4 squared plus 7 squared. We know that my r value always has to be positive, so I'm not going to do a plus minus on my square root here. I'm going to do 4 squared plus 7 squared. I get 65. I'll just keep that exact. R is going to be the square root of 65 because I might not want to round it off. And this was just, I'm not sure why I decided to find the sine of theta. I guess I just wanted to present this approach before we actually needed it. We could either use the tangent ratio. We know that the tangent of theta is going to be the ratio of kicks or ticks, y to x, 7/4. Or we could use the fact that we know that the sine of theta is going to be 7√65. Now, we might be able to simplify root 65. We might be able to rationalize this, but we don't really need to. I just want to point out here that if we calculate theta by doing the inverse tangent of 7/4, make sure you're in degree mode. And let's stop before I hit equals and look at this angle and estimate it and say it looks like this angle is probably maybe like about 60 degrees. When I hit equals, holy cow. It's a pretty good estimate. Theta is about 60. Did it say to the nearest degree? Yeah. It's about 60 degrees. Okay, my calculator has calculated. Imagine someone goes out and draws a triangle where they measure over 4 meters, up 7 meters. They should be able to measure with a protractor, and then they imagine that they programmed it into my calculator. It's not really what's happening, but that's kind of how it works. Let's do the same thing here. Let's take the inverse sine of 7 divided by the square root of 65, and we get the same answer. Okay. We might see spots where trig ratios give us different answers, though. That's why the sketch is so important. Should feel an awful lot like doing SOHCAHTOA in the first quadrant. This is where things change. Let's sketch an angle that passes through the point -3, -9. Maybe I'll make this scale like 10, -10, -10, 10. So if I go left 3, down 9, sketch your angle first. Do not touch your calculator first. And then predict or estimate. I remember I've worked tutoring with students in elementary school. The lessons that most math-inclined people hate the most are questions where they're asked to estimate, because sometimes they can just see what the answer is. It is a very valuable skill here. Let's keep in mind that we know that theta is in quadrant 3, which means that it has to be between 180 degrees and 270 degrees. We know this to be true. Our calculator will not tell us this. Okay. We're set up to use the tangent ratio. I'm just going to jump in and use it this time. I know x and y. Tangent ratio is pretty popular for that reason. Say the tangent of theta is going to be the ratio of -9 to -3. Let's think about, I think students would benefit if they understand how their calculator is programmed. When we type in the inverse tangent of -9 divided by -3, our calculator is going to divide -9 by -3 first. It's going to reduce that down to 3 wholes, or 3/1. Our calculator doesn't know that the angle is in the third quadrant because our calculator is not smart. We know that theta is in the third quadrant because we were smart enough to predict our answer before we just trust the calculator. That's a big change here. That I don't think happened in 3M. If you took 3U, you might be used to this, though. Your calculator isn't as reliable as it used to be. I'm going to type in -9 divided by -3, but my calculator still doesn't know what quadrant our answer is in. My calculator is programmed to give me the answer closest to 0. I was about to write down theta equals 72 degrees, but I know that that's not theta. So here's what I suggest you do for proper communication. Yeah, I'll introduce you to beta. Just label this angle something else. In fact, I'm going to write down that this is what I asked my calculator, but I'm using this other symbol because I don't trust my calculator, and I don't think you will either. It's a useful tool, and you're going to need it, but it doesn't seem to always give us the answer that we want. Just like if I was trying to solve when is x squared equal to 16, and I just say, oh, okay, well, I need my calculator to tell me that the square root of 16 is 4. My calculator doesn't know that I'm solving a quadratic that has 2 solutions, because my calculator is not smart enough to sketch and say, oh, are you solving a quadratic equation? Do you need 2 solutions? When we were solving power equations, we used sketches to catch how many answers we had. We're going to do the same thing here. Sketch it to catch it. It'll work again. Our calculator tells us 72 degrees. Now, our calculator's not wrong. The tangent of 72 degrees is very close to 3. Oops. Tangent of 72 degrees is very close to 3 because our angle and 72 degrees share or are related by their related acute angle. In this case, our calculator gave us the related acute angle. It's up to us to figure out how we're going to find theta. And your sketch will tell you. You're not memorizing, oh, is it 180 degrees minus 72 degrees or 360 degrees minus 72 degrees? No, you look at your sketch and you can see that theta is going to be the quadrant 3 angle. That has to be between 180 degrees and 270 degrees. So it's going to be about 180 degrees plus 72 degrees. It's very easy to just write down 72 degrees, especially if we come from a course where our calculator is always giving us the right answers. It's also very easy to see that 72 degrees is not the angle that we're looking for. Okay. If I take the tangent of 252 degrees, the answer is very close to 3. It's not exact because I have rounded off when I approximated the related acute angle. Okay. In example B, we found beta, the related acute angle, instead of theta. Beta and theta are related to each other. If we could find the sine ratio, the cosine ratio, the tangent ratio of beta, it's going to be the same as finding or related to finding the sine, cosine, and tangent for theta. It's not the same. Okay. We'll save this for another day, but if we had, say, done the sine ratio here, our calculator would have told us this angle down here. It would have said negative 72 degrees. If we use a cosine ratio, our calculator would have told us this angle right here, 108 degrees. So there's not always a way to get the answer out of your calculator. There's a pathway. The calculator will tell you what you need to do to get the answer, but it's your job to get the answer. Okay? Practice this a lot and check your answers instead of just trusting your calculator. Try it out.